This conference will now be recorded.
Hello everyone. The topics that we are going to cover today, it's enthalpy of atomization as it is seen here, and then there is bond enthalpy, lattice enthalpy, standard enthalpy of solution, and if time permits, standard enthalpy of dilution, and also enthalpy of neutralization. So it is basically different types of enthalpy. What is enthalpy? That is a new state function that we have already it is introduced in the last class already. Now basically we are focusing on how many different types of enthalpy possible, and it depends on the type of reaction. Okay, so here we have standard enthalpy of atomization. So this will be the standard enthalpy change in which reaction where atomization will take place, and in that reaction the enthalpy change before and after reaction, that is actually the enthalpy of atomization, and if it is under standard state it will be called standard enthalpy of atomization. So as a definition we can say it is the amount of energy change or enthalpy change when 1 mole of a sample, now this sample, it may be molecule, it may be element, it may be compound, anything is fine, and it will be dissociated into atoms. So that is why the process is called atomization, and obviously under standard condition. Now this value, it is always energy requiring process, that means you have to supply energy, so that is why it will always be a positive value. Now if we see examples, here we have total 3 examples. Suppose we have elemental sodium metal. When I'm saying elemental, that means it is in elemental form. And sodium under normal condition, it is solid. So in bracket, the physical state mentioned is S. Now it is already in atomic form. But don't think that there cannot be any atomization. Basically, when it is atomization, now the physical state is changed from S, solid, to gaseous state. Because when we consider this process atomization, it should be in gaseous state. So here it is not diatomic or triatomic, it is already monoatomic, but it is in solid form. So from solid state, now it is converted to gaseous state, and obviously it is also now monoatomic. In this process, the enthalpy change is known as enthalpy of atomization. This value is given. So here this subscript A, it is A for atomization, and this not value, which is the significance of standard state. Now come to the second statement. Second example. Fluorine. Fluorine under normal condition gaseous, and it is diatomic molecule. It is not monoatomic. That is, the natural form is diatomic molecule. Now you will break the F bond. You will get 2 fluorine atoms, and gaseous state, both are same before and after. So in this case, 79 kilojoule per mole is the enthalpy change. Then, so this is already in elemental form, element. So in bracket it is mentioned in the definition, first statement, molecule, element, compound, anything may be there. So these 3 examples you can understand. It may be element, it may be molecule like F2, and then we have taken a compound of carbon and hydrogen. So in CH4 molecule, that is methane, there are basically total 4 carbon hydrogen bond, right? So all this, that is total 4 hydrogen atoms we should get from CH4, and 1 carbon atom we should get, and all should be in the physical state G, that is gaseous. Now in this case the value is obviously high because 4 bonds are present, so it is more energy requiring process. And observe one thing, all are positive because it is always positive value. Now enthalpy of atomization, in some cases you can also call it enthalpy of sublimation. Suppose when you are starting this process, the starting point, it is already elemental solid. So this is basically applicable for the first example. See, for this example you can apply this. So this process, sodium is converted from solid state to gaseous state. You can also call it sublimation process, because sublimation means direct conversion from solid state to gaseous state, and here it is actually happening. So though it is atomization, according to the definition of atomization, it is atomization, but only under this special case when we are starting from elemental solid, Just like the sodium example, you can also take any other solid which is already in elemental state, that is monoatomic. Then also you can apply the same thing, that is for any elemental solid, enthalpy of atomization, it is same as enthalpy of sublimation. So for the first example, instead of saying that this 108.4 kilojoule per mole, suppose you are saying that it is not enthalpy of atomization, it is enthalpy of sublimation, then also you are correct. So you can use anything, but it is applicable only for elemental solid. So here, suppose we have this elemental solid, and now I am writing here sodium S, and this is the vapor form, that is Na, gaseous. So this change, that is this blue arrow, if you follow, this is basically del H of sublimation, or you can also say here del H of atomization. Not sign will be there if it is standard state. Now another way also you can consider this change, that is, suppose instead of direct conversion to vapor, you are converting the solid first to liquid state. So that enthalpy change should be called del H fusion. Fusion we have already covered in the last class. So this is solid to liquid state change, which is basically melting, or you can say fusion. So the enthalpy change for this fusion, that is denoted by del H fusion. Now from liquid state you are moving to vapor. So this is solid, this is liquid, and now you are moving to gaseous. So this change, that is basically del H VAP. Okay. So in this case, this del H sublimation, this is basically summation of these two, or you can say del H A, that is summation of del H vapor and del H fusion. So it is not that for elemental solid enthalpy of sublimation, enthalpy of atomization, you can use any of this term. Or another point is that for sodium metal, not just sodium metal, it may be for any other metal also, where you can stepwise move towards vapor. That is, rather than directly moving from solid to vapor, suppose first you are changing the state to liquid, then from liquid you are going to vapor, then you can say that enthalpy of atomization, it is basically the summation of enthalpy of fusion and also enthalpy of vaporization. Del H fusion, del H vaporization, which is equal to sublimation or atomization. Okay. Next is bond enthalpy. So this is also something enthalpy, but in this case, either we will break the bond present between two atoms, or you can form the bond. Now, if you want to break any bond, suppose I am considering there is a bond present between two atoms A and B. If you want to break it, you have to provide some energy. That is in general true for any bond. And similarly, if from A and B individually AB bond is formed, that is the reverse process, now there will be release of energy. So you have to provide energy when you are breaking the bond, and there will be automatic energy release when the bond is formed. That is the reverse process. So from AB you are making A plus B. That is one process. Another process is the reverse process. So in the second process, there will be release of energy. So energy will be negative, and in this case, it will be positive, basically daily, that is energy change. Now, if the bond is very strong, obviously more energy released will be there when the bond is formed. Or you can say in reverse way that when the bond is very strong, you have to provide very high energy. So whatever way you say, ultimately it is same thing, right? So in this case, suppose when the bond energy is released, suppose I am saying it is 30 kilojoule per mole energy is released minus. So when you are considering the reverse process, obviously now the sign will be plus 30. Now in bond enthalpy, you have to consider two different terms. Now that depends on, that is, what is the nature of the molecule. Suppose if you are considering a single bond, then you can use the first term, that is bond dissociation enthalpy. But suppose in a molecule there are many, that is same type of bond. Suppose I am saying carbon hydrogen bond. Now there may be more than one carbon hydrogen bond in a particular molecule. So in that case, it is not single CH bond, it is more than one CH single bond, or suppose OH bond, or suppose CC bond, whatever it is. But it is same type of bond present in more than one number. So in that case, you have to take average. So another term is there, which is mean bond enthalpy. So the first term, that is bond dissociation enthalpy, you can apply it for any diatomic molecule. Suppose we have A2, and in this case you just have to break the single bond that is present between two atoms. So it is for just one atom. So if we take that example, it is applicable for diatomic molecules. The bond dissociation enthalpy, that is the first term, it is the change in enthalpy when one mole of particular covalent bond, that is a particular time, that will be broken in the gas phase obviously, and it is applicable for diatomic molecules. And you can also say it is same as that of enthalpy of atomization. Now why I am saying so, just go back to the previous slide. In the previous slide, if you focus on this reaction, it is basically what you are doing here. You are basically breaking the single FF bond which is present in diatomic F2, right? Now here also you are doing the same thing, right? For any diatomic molecule, you are doing the same thing. So you are breaking the single bond present that is between two atoms, and that is why for diatomic molecules it is basically same as enthalpy of atomization. So here we have some examples. H2, here we are breaking the single bond that is present between two H atoms, and all are in gaseous state, so you can also call them enthalpy of atomization. Okay, then we have another example, chlorine. So these two are written in reaction form, but here we have some that is two different atoms we have taken. H is common this side, and we have taken some other elements. Basically we have taken some halogens, right? And in the right hand side you can see even multiple bonds are there. So when it is multiple bond, that is double bond or triple bond, obviously now the energy is very high. So here the energy is given in the form of positive sign. So which means what? If you consider this process, in this process you are basically breaking the HH bond, or you are breaking the Cl-Cl bond. So you are breaking bond, that means you are supplying energy. So obviously it will be positive, endothermic process. But suppose if you are considering the reverse process, you are moving from this side to this side, now obviously same value, but now it will be negative. Okay, so some values are given, so from which you can understand, you can have some idea how the values, what are their normal range. Okay, so this is for the first type, diatomic molecule bond dissociation enthalpy. But suppose there is more than one similar type of bond present, and that is applicable for polyatomic molecules. So now you have to use the term mean bond enthalpy or average bond enthalpy instead of saying bond dissociation enthalpy, because now the bond dissociation enthalpy is different for different bonds within the same molecule. Now it is calculated by dividing the total bond dissociation enthalpy by the number of bonds broken. How many number of bonds present? Here we have taken the molecule CH4. So here we have total 4 carbon hydrogen bond. So when you are breaking the first bond, you have to provide a specific amount of energy. Now you are left with the fragment CH3, and from CH3 again you will break another CH bond. So don't think that now the second time the energy that you have to provide, it is same as the first. No, it is not same. Now you will get the fragment CH2 and H. Now from CH2 you will again break. So in each time it is true you are breaking CH bond, but the value will not be same. But here the equation that you are seeing, that is actually the overall process. Overall process, if I write together, all the steps together, basically from 1 mole of CH4 you will get 1 mole of carbon and 4 moles of hydrogen atom. All are in gaseous. So in this case, this is the amount of energy we have to provide. Now individually if we see, so here though all the four carbon hydrogen bonds are identical in bond length and energy, because there is a specific bond length, but the energy is required to break individual CH bond in each successive step not same. So you can see the values for the first CH bond. When we are breaking, this is the amount of energy we have to provide. Now the next, that is, now you are left with this fragment. From this fragment, when you are again breaking another CH bond, now you have to provide another amount of energy. So in this way, total 4 values you can see. If you add all these values, you will get 1665, which is basically the overall process. That value already shown there. And if you want to get the mean value, basically you have to divide this 1665 by 4, which is 416 kilojoule per mole. So in this way we can calculate it. Now here CH bond, from CH4 we are getting it is 416. But suppose you have another molecule where also carbon hydrogen present. Suppose I am saying C2H6 ethane. There are also carbon hydrogen present, and same process you have to follow. Just here basically you have total 6 carbon hydrogen bond, and you will consider all the bonds, total enthalpy change, then you will divide it by 6. Then also you will get some CH value. Now that CH value and this CH value, they are actually more or less close to each other. They are not differing very high from each other. Come to this side. For any chemical reaction, the estimated change in enthalpy. Now suppose we have any chemical reaction. Just I am saying X plus Y, it is producing A plus B. So it is any chemical reaction in general. Now for this reaction, if you want to calculate enthalpy change for the reaction, R means reaction, R for reaction. So in this case, what you will do, first you will take all the bond enthalpies from the reactant side. That means bond enthalpy for this starting material and Y, though it is written X and Y, but there may be any two atoms present together. I have just written in a simplistic manner. So you just have to consider all the bond enthalpies in the reactant side first. Take all the bond enthalpies minus summation of bond enthalpies in the product side. This difference will give you the enthalpy of reaction. Now we have already seen that enthalpy of reaction we can calculate from enthalpy of formation also. That we have already seen, probably in last class or the previous, I can't remember exactly, but that we have already seen. But suppose if you do not have enough information about del H F dot, that is, suppose you do not have the data enthalpy of formation, then this relationship will help you to calculate enthalpy of reaction. So that is, it is written here, this relationship is useful when the required values of enthalpy of formation. Suppose enthalpy of formation for XY, YZ, AB, you do not have that data. So what you will do, another alternative way, you can do this one, that is bond enthalpy, that is based on bond enthalpy, you can do this calculation. And be very careful, it is a bond enthalpy summation. First it is reactant side, you have to subtract, then it is summation of the product side. So don't put product first. So why it is first? Because when it is reactant, in reactants the bonds are basically broken, and if you consider the product side, their bonds are actually formed. Now when it is broken, that is basically amount of energy that you have to provide. Okay, so it is basically some plus form, and in the product side the energies are basically liberated. That is, the energies that bonds are formed, that is actually the liberated energies. So that will be considered later. So when we will solve problem, it will be clear to you. So here we have a problem. Standard enthalpy of formation for ammonia. So when you are trying to form ammonia, you will start from nitrogen and you will start from hydrogen gas. That value is given. Some more informations are there. Enthalpy of formation of hydrogen from its atoms and that of nitrogen. That means enthalpy of formation of nitrogen, that is given. minus 712 kilojoule per mole. From this, you have to find the average bond enthalpy of nitrogen-hydrogen bond. So in ammonia, there are basically total 3 nitrogen-hydrogen bond. So first we'll focus on these two values. Enthalpy of formation of H2. It means what? It means you will start from Hg, Hg, you will get H2. So for this process, the value is given minus 436. I'm not writing the unit, all are in kilojoule per mole. Now, if it is so, for the reverse process, now reverse process is where H2G, you are breaking to 2 hydrogen atoms. Now, this process is nothing but enthalpy of, that is bond enthalpy, right? Enthalpy of atomization also you can say, but here I am saying bond enthalpy. So, bond enthalpy for hydrogen, that will be plus 436, because this sign is negative. So when you are considering the reverse reaction, obviously it will be positive. Similarly, if we do the same thing for nitrogen, two individual nitrogen, you are getting minus 712. But if I am considering the reverse reaction where you are getting 2 nitrogen atom separately, now in this case the value will be plus 712 kilojoule per mole, right? So these two values will help us for in the final step. Next, we will write the equation for enthalpy of formation of ammonia. Now, enthalpy of formation, if you remember the definition, it is basically the enthalpy change for the formation of 1 mole of the compound. So in the right hand side, I will write 1 mole ammonia. Now in 1 mole ammonia, there is basically 1 nitrogen atom. So in the left hand side, you will write half N2. You cannot write single nitrogen atom. That you cannot write. Why? Because according to the definition of enthalpy of formation, it is the enthalpy change for the formation of 1 mole of any substance starting from the constituent elements. Now, constituent elements of ammonia is nitrogen and hydrogen. And nitrogen and hydrogen, under normal condition, they are diatomic gaseous molecules. They do not exist as single nitrogen or single H, right? So that is why the natural form you have to take. So that is why I have written N2. But as it is only 1 nitrogen atom required, I have given the coefficient half. Similarly, you just need 3H. So what you will do, you have to write the coefficient as 3 by 2 H2. This is also G. So for this process, the enthalpy change, that is given minus 46. Okay. Now, we have to find the bond enthalpy of NH. That means 3 NH bonds are present here. So now we will apply this equation. Which one? This one. Bond enthalpy is reactants minus bond enthalpy is products. So if we do so, because this is enthalpy of formation of ammonia, but you can also say that it is as if equal to del HR. Because if you consider this reaction, for this reaction, it is the enthalpy change del HR minus 46. You can also call it in another way that it is enthalpy of formation of ammonia, but it is also del HR. That is, here the reaction type is enthalpy of formation. So that is why you can use both the terms. In general, you can say it is the enthalpy of reaction minus 46 for this particular reaction, or you can say it is the enthalpy of formation of ammonia. So for this, if we apply that whatever we have seen in the previous, so minus 46, that is del HR. Now summation of all the bond enthalpies that is present in the product side. So here we have to take bond enthalpy reactant side minus all the enthalpy change in the product side, P. Now in the reactant side, we have N2 and H2. Now for N2, 712 plus 712, that is actually the value that we will put here. So in the reactant side, it will be half into 712, then 3 by 2 multiplied by 436. So this side we are done. Now come to the product side. Now in product side there is basically 3 into bond enthalpy of NH bond. It is basically ammonia, but in ammonia there are total 3 NH bond, right? So for single bond, if it is del H Be, because ultimately we have to find average bond enthalpy of NH, but we will write 3 because there are total 3 NH bonds present. In this case, it is not 3. It is only one HH bond, one NN bond. But in this case, it is 3. So that is why I have written multiplied with 3. So finally, it will be, that is half 712. It is 356 plus 654 minus 3 into, I am writing here, bond energy or enthalpy of NH bond. So if you bring this quantity, that is, you can do anything basically. So I'm directly writing bond energy of in each bond, that is actually equal to 46 plus 356 plus 654 divided by 3, and after calculation it will be 352. So that will also be positive. So this is the correct option, that is option C. Basically it is a stepwise you have to think when solving the problem, because the way the problem is presented, it is a little bit confusing. Several different terms are used, and why it is confusing, because sometimes we say enthalpy of formation, sometimes we use the same term for enthalpy of reaction. So first time when you are learning this, so there may be little confusion, that the more you will practice, then you will be habituated with all the terms, then it will not be very difficult to you. So you have to practice a lot, then it will not be difficult. Option C is the correct option. A, B, a particular compound, then we have A2 and B2. So all these three are diatomic molecules. In the first case, it is heteroatom, but A2 and B2 same atom. If the bond enthalpies of A2, AB and B2 are in the ratio 1, 1, 0.5. So A2, AB, B2, a ratio is given for their enthalpy 1, 1.5, that is 1, 1 half. So if for A2 it is X, then for AB also it is X, but for B2 it will be X by 2. Now if we write the equation, because it is asking that enthalpy of formation of AB starting from A2 and B2, that value is given. So suppose here I am writing A2G, though state even if you not write, it is fine. So in this reaction, the enthalpy of formation of AB. What is the definition? Enthalpy change for the formation of 1 mole of AB. Now if you want to prepare 1 mole of AB, obviously it will be half. This will also be half, right? Now as we know, that is for total enthalpy change, if a standard state or even if it is not, that is actually equal to summation of bond enthalpy in the reactant side minus del H product side. Now in the reactant side we have A2, but it is half. So it will be, we have to consider X by 2. Then we have B2. Now for B2 it is X by 2, but there is also a coefficient half. So half into X by 2, it will be X by 4. And for AB also it is X by 2. Sorry, it is X as it is given here. Now we will put it here. This side it is minus 100 kilojoules because that is already given in the question. And in this part we will write X by 2 plus X by 4 reactant side minus X. So from this you will get, this is 4. So 2X plus X minus X. So it will be 3x. So if you do this final calculation, you will see it will be minus 3x minus 4x by 4. That means we are getting minus 100 minus x by 4. Minus minus cancel. So x is equal to 400. So it is asking what is the bond energy of A2, which we have considered x. So basically we need the value of x, which is option D, 400 kilojoule per mole. Enthalpy of atomization of bromine liquid. Enthalpy of atomization of bromine liquid, because under normal condition bromine is basically liquid, that is given x kilojoule per mole, and the bond enthalpy for bromine molecule is y kilojoule per mole. We have to find the relationship between these two, whether they are equal, whether x is lesser than y. There is no relationship exists, option 3, and option 4 is reverse of option 2. Now, when it is atomization from bromine liquid, basically we will be getting 2 Br atom in gaseous state, right? So see, this is the process, bromine at in liquid state. When you are considering del H atomization, I am writing here del H A. This is actually x kilojoule per mole. Similarly, the other process that is given, bond enthalpy for bromine. Now for bond enthalpy, what is the definition? You have to consider it in gaseous form. It is not that the natural form is liquid, so you will consider liquid. No. When it is bond enthalpy, you have to consider the starting, where you are starting, that should be G. So bromine G, and then it is converted to 2 bromine, because we are breaking the bond between Br. We are getting 2 bromine. So for this process, the corresponding enthalpy change is Y. Now, relationship between X and Y. One thing you have to notice, when you are converting bromine liquid to 2Brg, this is the final state, right? Now in the second process also, if you look at the final state for both the process, it is basically same, but the starting point is not same. That means, first if you consider bromine liquid, you have to convert it to bromine G, and then bromine G will be 2Brg. That means X should be greater. So see, if you consider stepwise manner, bromine liquid, first it is converted to, it is basically vaporization, del H, vaporization, you are converting to G, and then from bromine G, this is actually the bond enthalpy, which is this process. So for this process, it is corresponding enthalpy change is Y, and here for this process, what is the enthalpy change? That is not given, that we do not know, and that you don't have to find also. And if you move directly from this to this, then it is del H atomization, which is X. So X is covering this whole, that is, suppose this is 1, this is 2, this is 3. So del H atom X means you are moving from 1 to 3. But when it is Y, you are moving from 2 to 3. So obviously X is greater than Y. So del H atom, which is X, it is summation of these two processes. This process value we do not know, but one thing is clear, X is greater than Y. Fine. So this should be the correct option. X is greater than Y. So we have to know all the definitions properly, because it is true they are little confusing, and they are sometimes we for special reaction they are same. For example, for elemental sodium, enthalpy of atomization is same as enthalpy of sublimation. So be very careful that what type of processes are given, and you have to read the question carefully, what it is actually saying, enthalpy of atomization or enthalpy, though all are enthalpy, but processes are different. So when it is atomization, you are starting from liquid, you are moving to gaseous. Here also you are moving to bromine gaseous, but starting point is not same. So these are the subtle difference that you have to keep in mind. Okay. Lattice enthalpy. So this is also another kind of enthalpy. Now this is the enthalpy change involved to completely separate 1 mole of solid ionic compound. So remember, it is applicable for only solid ionic compound, not for any other type of compound, not for liquid, not for gaseous, solid as well as ionic. Then only you can apply this term. So when you have a solid ionic compound, you are applying some energy and then you are breaking the constituent gaseous ion. Remember, the final state should be gaseous ions. So if I am saying NaCl solid, final state should be Na plus ion, that is cation, Cl minus anion, but in gaseous form. So for this process, the energy that you are supplying, that is actually lattice enthalpy or enthalpy change. Sometimes it is also called lattice energy. Now this is a measure of the forces present between ions in an ionic solid. So when these ions are present in ionic solid, like this, so there is some forces present between them. Now if the force is very strong, you have to provide more energy. That means when the lattice enthalpy value is very high, you can understand that the interaction between them is very strong. So you have two compounds. Suppose you have NaCl, you have KCl. So for NaCl there is one particular value of enthalpy. For KCl there is another value. You can compare these two and you can understand in which case the forces present are stronger. So greater the lattice enthalpy, stronger is the forces. Okay. Now lattice enthalpy we cannot measure directly. So why we cannot measure directly? Because it involves so many different steps. You are basically starting from NaCl solid or KCl solid, and final state you are getting Na plus in gaseous state, you are getting Cl minus in gaseous state. So it is, don't think that it is a single step process. Single step we can do it if we can provide energy, but there is so many steps involved. For example, you have to start from, that is, if you consider only sodium, then from sodium, from solid state you have to convert to gaseous, then you have to remove electron, it will be now converted to Na plus, like this. So many different processes are involved. So lattice enthalpy cannot be measured directly, it is not so easy also. That is why we will take the help of Born-Haber cycle. So this is a cycle which is based on Hess's law. Now before going to Born-Haber cycle, try to understand Hess's law. It is very simple. Enthalpy, we are talking about enthalpy. Now enthalpy is state function, and for state function you can add the values, simply add the values. For example, suppose you want to move from one state to state 4, you can directly do so, and suppose here the process is delete. But suppose you are first moving from 1 to 2, here the delete is 1, then you are moving from 2 to 3, here the delete value is delete 3, then you are moving to 3 to 4, here the value change, corresponding enthalpy change is delete. So this is 2, this 3. So this delete, this is basically summation of these 3, because directly you can move from this to this, but you are not doing so. First you are moving from 1 to 2, 2 to 3, then you are going from 3 to 4. So you are breaking the parts, but you can add all these values. So we will take the help of this. This is actually the Hess's law, and it also proves that enthalpy is state function. So this law states that the enthalpy change for a reaction is the same whether the reaction taking place in one state or a series of states. And this law is also, it proves that enthalpy is a state function, because only then you can do so, otherwise not. Now here, though in the first point the definition is given, but we have to remember two different terms sometimes used, and they are very confusing. So just to remove that confusion, I will make it clear. So what is the confusion that can arise? Suppose you are starting from NaCl solid, you are moving to Na plus G, Cl minus G. So this is stabler state. This is compared to, suppose this is state 1, this is state 2. So state 1 is stabler state. And here also you can see energy is increasing as you are moving in the upper side. So when you are moving from 1 to 2, you are breaking NaCl So obviously you have to provide energy. So this value now, this is basically the difference in energy between the state 1 and 2. But if you want to move from 1 to 2, you have to provide this energy. So it will be a positive value. But suppose if you are doing the reverse process, you are moving from 2 to 1. This is 1 to 2 and now you are moving 2 to 1. So you are combining these two. You are getting NaCl. That is a reverse process. Now in this case, the same value is applicable, but now it will be minus 787 kilojoule per mole. So it doesn't matter which path you are going, because numerical value is always same, but whether you are applying the providing energy or you are getting some released energy, that depends on whether you are moving from 1 to 2 or 2 to 1. Fine. Now which path you are following, depending on that, two different terms can be used. Though in general we use the term lattice enthalpy. That is the topic we are discussing. But when you are moving from 1 to 2, you are basically dissociating. So in this case, we will use the term lattice dissociation enthalpy, or sometimes it is said lattice disruption enthalpy. You are disrupting it. The amount of energy needed or required to split up lattice into scattered gaseous ions. The value is given plus 787 kilojoule per mole. But if you are moving from 2 to 1, so this is from 1 to 2. That is the movement. If you are doing the reverse one, now you are moving from state 2 to state 1. Here we are using different term, though the numerical value is same. But now you are using lattice formation enthalpy, because now from individual gaseous ions you are making the ionic solid. So in this case, energy will be released. Amount of, because it is moving from some unstable state to stable state. So energy will be released. Amount of energy released when lattice is formed from its scattered gaseous ion, that is separated gaseous ions. So for NaCl it is minus 787 kilojoule per mole. So don't be confused between these two values. It depends whether you are moving from ionic solid to gaseous ions or the vice versa. Okay. Here we will discuss the whole process, that is Born-Haber cycle for sodium chloride. So see what we are doing. We will start at this point. Okay, so just focus on these two. Na in solid, suppose you have taken elemental sodium, don't look at other portions, just focus on this where I am pointing. From sodium solid you are making sodium gaseous. So this is basically sublimation, right? Or you can say it is atomization enthalpy, both are same. So for this process, the amount of energy required plus 107. So this is the atomization enthalpy of Na. Del H sub, that is mentioned here. Del H sub means sublimation enthalpy. Now, next what we are doing? Del H IE. Now what is del H IE? It is also enthalpy change, but it is ionization energy. That means from sodium G, now we are making NaG. That is physical state same, gaseous, but you are removing one electron. So for this process, you are removing this electron, you have to provide energy. This is basically ionization energy. In the periodic table chapter, we have seen what is the definition. So you are forcefully removing some electrons, you have to provide energy. So for this process, del H IE, and the value is 496 plus 496, that is the value mentioned here. So this is the second energy that you have to provide. So del H sub, del H IE. Next is, now come to the chlorine side. So when it is chlorine, you have to provide del H dissociation. Why del H dissociation? So here it is half chlorine gaseous. That is the natural state of chlorine. It is diatomic. But you have to break the chlorine-chlorine bond. So del H dissociation. and for that you have to provide energy, which is plus 1 to 2. Look at the left hand side. In the box it is mentioned plus 1 to 2 is the atomization enthalpy of chlorine. Next, what energy we have to provide? It is del H electron affinity or electron gain enthalpy. That also we have seen in the periodic table chapter. So in this case, what we are doing, from chlorine G, we are forcefully adding a electron, and as a result, now it will be Cl minus. So fine, and for this, it is basically release energy, because ionization enthalpy, most of the cases it is negative. So when it is from chlorine atom, you are adding one electron, it is reaching the noble electron gas configuration, which is a stable species. So as you are moving from unstable state to stable state, energy will be released. So that is it is minus 349. Look at the left hand side, it is a fast electron affinity. Why written fast? Because if you do the same process, that is you are adding one more electron to Cl minus, though that is not feasible, but I'm just saying, then it will be second. But we just need fast electron affinity. So that is why it is written in the left hand side, it is fast electron affinity. So finally, we have at our hand these two species, Na plus gaseous, Cl minus gaseous. Now remember, lattice formation enthalpy, what it says, when from individual ions in gaseous state you are making this solid, that process is lattice formation enthalpy. But it will be negative because you are moving from unstable state to stable state, right? So finally, we have the positive and negative ions that we can convert into solid NaCl using the lattice formation enthalpy. So we can add all these values. But here you have to remember one more thing. See, these values also there. What it means? Minus 411. Now this is basically enthalpy of formation for NaCl. Remember definition of enthalpy of formation? It is the enthalpy change for formation of 1 mole of any substance. So NaCl natural form is solid. So when you are making 1 mole NaCl solid, starting from its constituent elements in their natural state. Constituent elements of sodium chloride is sodium metal, natural state solid. Another constituent element is chlorine, natural state, diatomic molecule and gaseous. So these two are the natural state from where you are getting this, and this is basically del HF, enthalpy of formation of NaCl. Now here the direction is towards this side. So if we apply Hess's law, applying Hess's law in these two different routes, what it means, two different routes. Suppose this is a state 1, you are moving to state 2. This is the direction. But you can also move via all these steps that are mentioned here. So that is why one side it is mentioned in the left hand side of the equation, it is del HF naught. But okay, not sign, just ignore it, because for others I have not given not, though not sign should be there. So apply it for all. Otherwise don't apply for anything, because one is there is not sign given, another space, another enthalpy not sign not given, it is not right. Okay, either put it for all or don't put on any of this. So del HF on the left hand side, which is energy change for this process, and in the right hand side you can see all the processes are given. So I am erasing all this so that you can see it clearly. So in the left hand side, what values we have? We have del H sub, which is this process for sodium solid to sodium gaseous. Then we have del H dissociation, which is for dissociation of chlorine diatomic molecule. Then we have del H ionization energy, which is for this conversion Nag to Na plus. Then we have del H electron affinity, which is conversion of Clg to Cl minus. And finally we have Na plus Cl minus, together it is forming this. So this is actually lattice energy. Now suppose this value is unknown and you have known values of all the other del H, then you can put it, and from this equation you can calculate lattice energy. Now mostly when it is lattice formation enthalpy, that is when it is a negative value, we use the term U for lattice formation enthalpy. Though here it is not used, but here simply LE is written. But if you see somewhere U value, it actually lattice enthalpy. So it is minus 411, that is these values are given, and if it is so, then lattice energy, just keep it on one side and put all the figures on one side. So finally what you will get minus 787. So from this equation, the value of lattice energy you will get in negative form. Why? Because the diagram we have designed in such a way, it is basically from Na plus G, Cl minus G, you are making this stable ionic solid. So you are moving from unstable to stable. So obviously it will be negative. So in this way, directly we cannot calculate lattice enthalpy, but applying Hess's law, the Born-Haber cycle, this cycle that you are seeing in the diagram right hand side, that is actually Born-Haber cycle. So based on Hess's law, Born-Haber cycle we have, and then using Born-Haber cycle you can calculate LE value provided all the other values are known. Fine. Standard enthalpy of solution, another enthalpy change. Now we have to understand what it means. What we will see, obviously it is enthalpy change for this solution process, but what is this change? Definition is saying that del H sol naught, it is basically when 1 mole of a substance dissolved in a specified amount of solvent at constant pressure under standard condition. So look at this side. Suppose you have solid sodium chloride, and when, that is, you have added water, and now you have Na plus aqueous condition, Cl minus aqueous condition. Aqueous condition means Na plus, these ions are surrounded by several water molecules. Obviously the oxygen side will be facing towards Na plus, because oxygen side of water is negative. So like this, OH2, OH2. Similarly, Cl minus, that is also surrounded by many water molecules. So that is the difference between naked Cl minus ion and this. When in bracket it is mentioned AQ, that means it is surrounded by, that is anion cation both are surrounded by different water molecules. Fine. So for this change, NaCl solid converted to Na plus aqueous, Na plus Cl minus aqueous, the corresponding change in enthalpy is solution. Now they are in solution state. Now this enthalpy change value, it is related to del H lattice and also del H hydration. How they are related? Now del H lattice means what? That we have just finished in the previous slide. It means from NaCl solid, you are getting Na plus gaseous ion, Cl minus gaseous ion. For this enthalpy change is lattice enthalpy. Here we have written it in terms of del H. And suppose from these gaseous ions, now you are just changing this G state to aqueous state. They are already in plus and minus form. You are just changing from gaseous state to aqueous state. For this process, the corresponding enthalpy change, we call it hydration enthalpy, because most of the cases water is the solvent. So that is why hydration, this term we are getting from water. So suppose this is path, this is state 1, this is state 3. You can directly go from 1 to 3. For that enthalpy change del H solution. But suppose you are moving first 1 to 2, then 2 to 3. So via you are moving to via 2. So that is why summation of these two will be del H solution. So this relationship is very important, because suppose you are solving some problem, these two values are given, you can simply add them, you can get it. Or suppose del H solution, del H lattice given, this is unknown, you can also get it from this equation. So enthalpy change, that is del H solution, definition we have seen. But sometimes suppose we are doing a special case, infinite dilution. So enthalpy of solution, infinite dilution, when we will say so, when the enthalpy change is occurring because of the process, when you are dissolving, suppose you are dissolving NaCl solid in infinite amount of solvent, which is basically imaginary, but if we want to see this type of dilution, that is maximum dilution possible. So in this case, what happens? Interaction between ions, as they are far from each other, it is infinite dilution. Suppose one Na plus ion, it is far from other ions. So what will happen? The interaction between two ions, that is negligible. So this is a special case, but the definition will be like this. And then the third point, the value of lattice enthalpy, it can be used to calculate enthalpy of solution from this expression. So this expression you have already seen here. So here deluge hydration is the enthalpy of hydration. Definition is when 1 mole of ions, basically in gaseous state, undergoes hydration. For that process, the enthalpy change is deluge hydration. Okay. So based on this previous formula, here we have this problem, lattice enthalpy and enthalpy of solution. Remember the formula, we have seen the relationship deluge enthalpy, deluge solution, deluge hydration. So enthalpy is given 788 and enthalpy of solution given 4, right? So you have to find enthalpy, hydration, enthalpy. This is very easy. Simply put the formulas in the formula that I have mentioned. So from NaCl solid, you are moving to NaCl aqueous. So this is basically deluge sol. And this process is basically deluge Le, lattice energy. This process is basically deluge hydration. So these two, if you add, you get 4, because deluge sol, deluge Le, deluge hydration. So from this you can get deluge value minus 784. So option 2, that should be the correct option. So today we'll finish here. We are at the end of the session. Thank you for listening.